Hey, welcome back. So let's get on with it. We're going to apply the Bootstrap to something called bagging. Okay? Seems like that term might have to do with the bag we drew it out of, but no, it's just an amalgamation of Bootstrap aggregating. What is Bootstrap aggregating? Well, it's due to Leo Breiman, and it is the basis of a lot of ensemble machine learning. So what we do is we take the Bootstrap samples. We make a bunch of these samples. So this is just one Bootstrap sample. One time we took, so to be more clear about it, what you usually do is if you have n samples inside the bag, we reach into the bag and draw n times. Right? I kind of implied that with the math I was using, but I should say it in words. So we have n marbles in the bag. We reach into the bag n times and grab a marble, and we put it down and record it. And then we pick up that marble and we put it back in the bag. We replace it. All right, so if we do that sampling with replacement, we're sampling the same number of things that are in the bag, but as we just looked at, you're not going to get all of the elements, right? You're going to find that in one of the Bootstrap samples, you have 2 greens, okay, and no blues. In another one, we have 3 reds and 1 green, okay, so on and so forth. So each one of these Bootstrap samples is a resampling of the data that we already had. And in that way, we're getting a slightly randomized version of the data set that we had. We're going to pick the same data set, but we're going to get just a random subset out of that data. So you're going to use each individual Bootstrap sample to train its own classifier, and then we're going to use a voting system to combine each one of those classifiers, and that is bagging predictors. So I've pretty much set it, but here it is in pseudocode. So we're going to take n Bootstrap samples and we're going to loop around and do the sampling and train a classifier on the results of that sampling. And then we're going to run each one of those classifiers forward with a test set. And we're going to take the mode of the test set outputs of each individual classifier as our answer. So here we are. We're just filling in that bit. We're going to put in the mode voting for majority vote. And what is it that can go in each one of those slots? Anything, right? You can put whatever your favorite algorithm is inside. One thing that people commonly do is they will usually use relatively simple classifiers in there. We are unlikely to use a 17 nearest neighbors thing compared to maybe a 1 nearest neighbor, okay? Or we may use a decision tree, but we're probably not going to put a deep learning network in there. Why do we do that, by the way? Why do we choose simple classifiers? Well, there's a practical reason. The practical reason is that we're going to be doing this a lot, okay? When we're putting together ensembles, and if you do something that's computationally expensive, you're doing that computationally expensive thing a lot. Another reason is just the fundamental idea of the classifier, of an ensemble classifier, doesn't need a strong individual classifier. It's perfectly fine starting with relatively non-powerful, not very expressive, high bias classifiers and putting them together to make something better. So no reason to waste your energy. All right. So we have gotten already the idea that what is a bagging classifier? A bagging classifier is something where we take a bunch of bootstraps of a data set, we train a bunch of individual classifiers, And by the way, they could be different. I should have said that. Like all the different slots of the bagging classifier, you can put whatever you want in there. You could have, 9 of these kinds of algorithms and 4 of those kinds of algorithms. Whatever you want. It's all cool. Okay? It's like pizza. Just throw more toppings on it. Okay? So that aside, once you've done this bagging, you have an interesting situation. And why is that? Well, let's go back here. So what is not in our exemplar data set? Well, this one's not, and this one's not. This one's not, and this one's not, and this one's not. Our exemplar data set is only composed of these. Okay. So that means that all the ones it didn't see as training data, these could be test data. Ho-ho, right? And you start to see it. That is what the out-of-bag error is. Every time we build a resample, what we should do is, when it's time for doing something like a cross-validation, you don't have to do a cross-validation. You've already got the thing built in here. So how does that work? So you just run through the whole training set. You check every pair of inputs that are in the training set. And what we do is we construct a predictor by taking each one of those training set points individually, figuring out which ones of the predictors don't have that sample. So we just make a list of which ones don't have the sample, and then we check those classifiers and those classifiers only. And we ignore the other ones. And that creates something called an out-of-bag error. So here in this figure from Hasty, you can see that against a test set, right, the out-of-bag error is higher. It has a more pessimistic bias. The out-of-bag error is biased in the sense that it's not always going to give you the answer of proper generalization. And it's biased in a pessimistic fashion. It believes that errors are going to be worse than they truly are on the test set. Okay, so I mentioned the word bias a second ago. So I wanted to recap a little bit of our bias and variance topic, right? So we've already kind of talked about this at least twice, but it's a very important concept. So we have bias in terms of, are we on the target, right? So is the center of my distribution the center of truth? So this is low bias and this one's high bias. Okay, and that's true up here too. This one's got a lot more variance, right, compared to this, but the center of the distribution is just as spot on as in the left-hand case over here, right? And likewise, these two, they have the same center of the distribution, but just the different variance. All right. So I wanted to walk you through the math, which is the one thing I just kind of almost did once and didn't actually do. So let me do it properly here. So this is the page out of Hasty. You can go read it yourself. But what I want to highlight here is kind of like the key idea behind almost all of statistics. Okay? So we're going to assume right off the bat that there is a built-in underlying process that we are measuring. And that process has got a true deterministic nature. Okay? The process itself is actually deterministic, but it is corrupted by random noise that gets laid on top of that deterministic behavior. So that's where we get the form of this. Okay? So this is my random noise. And critically about this is that this random noise, especially in the standard linear setups, is supposed to be a Gaussian, which is mean of 0. Okay, its expected value of this noise is a Gaussian distribution flowing out with a mean of 0. So it's centered, the noise is centered on the true value. All right, so if we want to derive why there is a trade-off, why is it that when we turn up bias, we'll usually turn down variance and vice versa? Well, we can just derive that starting from the mean squared error, right? That's what this is right here. It's the outputs of the system, right? And the true values, y. So y minus the outputs of the system squared. That's the mean squared error. All right. Now, this is the derivation. This is skipping 19 steps in between each one of those steps. So that's why I'm going to show you a slightly different version of this. Okay. So let's take a look at these equations. So once again, you see the mean squared error there is the left-hand side of the equation. The expected value of truth minus prediction squared. Okay? Well, what we have to do is we just have to expand what's in that square out. All right? So number one, the number one element there is because the output y is defined to be the true function plus that epsilon term, right? So we are merely substituting y. Okay? So we're substituting that in that way. Now, now the next thing, number two, is a square expansion, okay? So what we're doing is we're expanding to do squares, and the linear property, we're also using the linear property of expectation, that so that the expectation of two things put together that are independent variables can just be an addition, okay? So how does that work? So the multiplications in here are going to fall out into the expectation here, right? That these terms, as we do the first, outer, inner, last, that we can move the expectation to the outside of each one of these. And we can do that because we're assuming that there is a linear independence in between the noise and the value of x, okay? So there's no relationship there. All right, then we start to just get rid of some things, right? So remember that we have this definitionally, that the expected value of the noise is 0. That is, that the noise is 0 centered. Okay? And that this is really just equal to the sigma of the noise. Okay? So we can simplify things down at that point. You know, this 0 term makes all this go away, and we are left with this. Okay? For now. All right. So what about, you know, we still need to expand out that last term, right? So that last term, equation number 3, we need to expand that out again. So to get after that, what we've got to do is we're going to do subtract and add by the expected value of f hat of x. Okay? So we're just going to throw that in there, okay, in order to do some manipulations that are going to turn out right for us in a minute. Okay? In equation 5, we expand the term inside the square, right? So the bias of E of f hat of x minus f of x is just a constant. Okay, we're subtracting f of x, which is a constant, from the expected of f of x, which is also a constant. So the two things being constant, right, we don't need them anymore. So applying expectation to the squared bias does not have any effect. Okay, so so in other words, the expected value of f of x is equal minus f of x squared is equal to the expected value of f of x minus f of x squared. All right. And then in equation 6, fundamentally what we're going to do is we're going to pull f of x minus the expected value of f of x, f hat of x, out of the expectation, because as we mentioned, it's a constant, so it can just transmute right out. And then lastly, we have 7 is because of the linearity of expectation, that we can move things around because they're linearly independent. Okay, and then we get that final one, 8. Okay, so at that point, we're left with, at 7, we can start to see definitionally that this is the definition of the variance of a distribution, right? It's the second moment. And this one is our bias term. It's the output minus the expected value of the output. All right, so there is a derivation. As you can tell, I had to read quite a lot of that derivation. This is exactly the kind of thing which so many people know the answer of, but relatively few people know how to make it work. And I'm going to include myself in that. But hey, no worries if you didn't follow all that. You can try to struggle through with various sources, or you can just go on with your life the way I did. But it is important to note that by doing this derivation, we have established that there is a bias variance trade-off, and that's why we have talked about it so repeatedly, because it is fundamental to any kind of statistical learning. And again, I should actually emphasize that we are particularly talking about the situation where we have this assumption, okay? And it's so key to realize that if you're trying to learn about something which doesn't fit this pattern, where there is not a single frozen process generating the data, and it's not just corrupted by zero mean noise, okay, that a lot of the basis that we've been talking about of how these algorithms work can go right out the window. And if you want to know how to mess up machine learning, you mess up machine learning by doing it on data sets that are, for instance, not stationary, where the process is not the same process now as it was 2 years ago. There'll be some evolution of the process where the constants are changing. Okay? Those kinds of things require special techniques, which have a special bit of mathematics behind them. All right, so finally, in the end, just to see the original version of this, we just combine equations 3 and 8, and we get the form that we saw in Hasty's book, where he left the proof as an exercise. All right, so what does that look like, right? We have a bagging system, an ensemble, which is, putting together a bunch of simpler classifiers to get better, we have said. How do we know it gets better? Well, we talked about the fact that we have that binomial distribution version to show us that for binary classification it gets better. But I also wanted to show you that not only is error reduced, but also we can reduce variance, okay? That's the other factor of doing an ensemble classifier. So here on the left, we have The left column is regression using a decision tree. It's the CART system, right? So if you remember CART, what it is that we're doing a tree, and the tree just learns that I'm going to guess the mean value of things inside my node, right? So as we split off, it's going to be like, something like x less than 3, yes, no, right? Then it's going to say something like, we're going to guess the value is 0.5, and if no, then we're going to guess the value is 0. Okay, so that's how you do regression with a decision tree, and I've obviously super simplified the process. Okay, but the important part here is that we're using a decision tree, which is a noisy system. Decision trees have a real issue, actually, right? They are so prone to overfitting. If you let them go deeper and deeper, they will just fit every single data point to itself, okay? So many trees, you stop them early to prevent them from overfitting. They're really prone to overfitting. So when we try to do regression with a decision tree, you can see in the red here, this is, the dark red is the training set. So we can see that the tree regression is fitting the data set exactly. It's running right through those dots. And obviously that is hyper overfit, right? We know that the underlying generating process is this sinusoid in cyan color. Yeah, blue actually, my bad. Okay, so the light red is showing test set going through, and what we can see is that when we look down below, right, so this is the tree, and we can see its level of error overall in red, and the bias term, we can calculate it, what it is exactly, using those methods we just showed. And we can calculate the variance term, which is in the green, which is kind of hidden behind the cyan, and the irreducible noise term. Okay, and we can see these are all quite high for this decision tree. So if we bag up, we have 50 elements in our bag, in this case, 50 different classifiers. What do we see? Well, let's look at those dark red lines there. So if you compare left and right, you'll see out here, it heads all the way to this point here, right? It's going to hit every single data point, smack on. So in the bagging tree version of it, we notice it doesn't go out to those points. It doesn't actually include them. It generally stops short of the most extreme version of things. Okay? And especially like down here, we don't hit any of those things down there. That's quite an interesting one. All right, so the bagging, the voting, right, where each tree, so we're doing a bagging system of the same kind of decision tree we used on the left-hand column, right? So we're going to take, here is one of these, and here is 50 of the same thing. Okay, so each one of those 50 trees, they all have a completely different data set they were trained on. It was all drawn from the same training data. It was Bootstrap resampled, right? And each one of those 50 trees has a different resampling of the same data points. Okay, what you see coming out the bottom is that green variance term has dropped way down, right? So it's come out from underneath that cyan noise term. Okay, and the flip side of that is that the bias, you would think, right, it's a trade-off. It must be getting higher. But no, the idea of the bias variance trade-off is that it is the usual thing, but it's not the only thing. In this case, what happens is that the irreducible noise actually is going up a little bit of a level. And it's what's absorbing that. So you'll see that actually the bagging tree actually has a slightly lower bias than the plain old tree. So both bias and variance are going down in this case. So the bias variance trade-off is not a deterministic thing, right? Other terms can absorb it, including the, irreducible noise floor. All right, but another important part to really realize is that here's what's going on. It's not letting this overfit so badly, right? It's not letting it overfit so badly. That is one of the fundamental aspects of what bagging does. All right, which leads us to our final few minutes to address the amazing and versatile random forest technique. So we've basically already explained random forests minus one element. We are going to do a bunch of Bootstrap resampling to make trees. Each tree gets its own Bootstrap resample. The thing is that now what we're going to do is at each decision point in constructing the tree, we're going to select a different random subset of the features for consideration. Okay, so, okay. So, actually, oh yeah, no, it is in a later one. All right, I got confused about what was in what slide where. All right, so here we are. Random forests, they were originally invented by Tin Cam Ho, who called them decision forests. And in this case, what we had was that there was a random subspace method, right? Each tree, the whole tree, got a different random subset of features. And the tree was constructed node by node, just using a data set that had a random subset of the training set's features. Okay? So that means that, right? Tree 1 gets the features, that's probably the wrong notation, but we'll go with it. Gets a notation, gets the features 0, 3, 6, 7, etc. And tree 2 is going to get the features, 0, 1, 3, 4, blah, 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 right? Each one being a random assignment. Now, just a few years later, Leo Breiman proposed what's become this canonical version of the random forest. So what happens there is that as you're building a tree, so here's tree 1, okay? As we're building the root node, we select the random subset of features, okay? So we're going to get features for node 1. I'm not sure how to notate this actually, but we're going to get a feature set, okay? Which is 0, 1, 3, blah, 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 okay? And as we're building the tree, we build the next node, okay? We get a different set of features, which is going to be 1, 9, 7, etc. Okay? Now, I drew right underneath my head again. So that's the random forest. We are at every single node selecting a subset of features to be available for the split. Okay? Available for the split. We're not splitting on all these features at each node, we're just putting them out there as candidates. And then, of course, the decision tree algorithm does what it always does. It picks out of those candidate features, it picks the one that's going to maximize what? Ooh, nobody wants to talk in class today. Well, right, it doesn't matter what you're maximizing. It could be the Gini impurity, it could be something else, right? For the case of the cart thing, it's going to be the Gini impurity. But it's going to maximize that split, is going to try to pick the element that's going to reduce uncertainty the most, right? It could be information, it could be doing the opposite, doing entropy, right? We can maximize mutual information, we could minimize entropy. I think I said that the right direction. Somebody can correct me later on Piazza. Or we can do the Gini impurity. But whatever it's going to do, we're going to pick the node at that point, which is going to do the best job to separate out class from class. Okay. Now, what is kind of a parameter of random forests is how many features are going to be selected at each node. We're going to randomly draw some number of features. One typical example is that we're going to draw log of the number of features in the whole data set. Another one is we draw the square root of m. Okay, and sometimes you can dial that down all the way to just random one. We're just going to use this one. Okay, I'm going to randomly pick the decision surface. So all those are things. Now, a note for implementation, right? So scikit-learn is our standard here, and it has a funky implementation that doesn't go all the way with Bryman's random forests. So they implement soft voting because scikit-learn loves to induce, they love a well-conditioned classifier, and they make almost every single classifier that they can output a probability estimate. Okay, so they use that, and they use a soft voting system instead of a hard voting system, which is what Bryman did in the original paper. Now, another cool thing about random forests is that you can use the Gini impurity or the entropy or whatever of a given node as a measure of its feature importance. All right, so nodes at the top of a tree, the root, right, are going to have the highest split value, right? They're going to have the biggest decrease in Gini or entropy when you go through that node. And that is an implication that those are the most important things to work on, all right? So if you want to know, you want to do something interpretable. You want to know, hey, classifier, that you have done some magic answer. How did you get to that answer? Well, remember, decision trees themselves are lovely easy, right? Decision trees, you can just turn them into logic rules. That is not true of a random forest. So the one way you can, well, one of the ways you can do something, I should say, is that you can just look at the impurity decrease at every given node and weight it and average it across all of the trees. And then you can normalize it to sum the feature importances to 1 if you wanted to be probabilistic about it. Okay? So in the same way that the coefficients of a linear regression give you an idea of the importance of the variables, and the rules of a decision tree tell you that, you can use this method to tell you about the feature importance. All right. Let's go ahead and just give you a quick intro to the idea that there's a Bryman's paper has this loose upper bound on performance. Okay, the generalization error PE is going to be less than this magic equation. I don't want to get into what this magic equation is. What I want to draw out is this relationship. So it's in terms of the average correlation among the trees versus the strength of the ensemble. Actually, that's not a good color. Let's use that one. Okay, versus the strength of the ensemble. So what you can see here is if you want to make sure that the generalization error is going to be low, you've got two terms there to deal with. The average correlation among the trees So decorrelating the trees is going to make the performance better. So the trees all make the different mistakes, right? They all make mistakes differently. They don't follow the neighbor and guess what the neighbor guessed for the marble jar, right? Each one makes its own mistakes, and the correlation among those trees goes down. That's going to help get better generalization. And the strength of the ensemble is also in this, so that you can end up, the strength in this case means how powerful is the system at overfitting, essentially, right? A very good overfitter, a 12th order polynomial, is going to be a very strong classifier compared to a linear classifier, okay? So there's a trade-off between these two elements that we can use to find the generalization error. And it leads back to that idea that we've got, we want to make the wisdom of the crowds work for us. Okay? So what are some features of random forest? I'm sorry, I thought I cut this old slide. That is not true. It's not unexcelled. It is, in fact, good enough, right? So the thing about random forests is that they're generally not very sensitive to parameters. So hyperparameter tuning, yes, you can, and you probably should, but don't expect to spend a huge amount of time on it, because mostly you're going to get the same answer from many regions of the hyperparameter space. And what's nice about random forests is that even though they're not kind of sensitive to the parameter space, they're pretty dang good, right? Things that are not sensitive tend to be poor, right? So like if you, there's no hyperparameters in ordinary least squares regression, right? So, it tends to not be the most powerful method of doing things. And that's the usual case. But random forests definitely punch above their weight in terms of you don't have to tune them very much. They're not sensitive to it. And they're still, they'll be in the top 10 answers for most things. It is, however, very efficient computationally. You can handle loads and loads of input variables, in part because it does feature selection itself. How does it do feature selection? Well, by following that impurity thing, right? If you go ahead and tell it that it can't grow the tree an endless depth, that we have to stop at a relatively shallow value, then it's never going to get down to the features that don't tell you much about the problem, right? It's going to reject them. They're not going to be in this shallow tree. Okay, so by doing that kind of thing, limiting the depth of the tree, limiting the number of leaves, then we can essentially do feature selection by following that greedy impurity split. So it also gives us estimates of what features are important, like we just kind of closed out with. And we have this internal unbiased estimate of the generalization error, which is coming out of the building process with the out-of-bag generalization. So it's an effective method also for dealing with missing data, because you can essentially infer what's missing using a tree approach. Okay. So, and also has methods for balancing. I kind of lost that at the end. You can also balance the class proportion. So if you have like a healthy and cancer patients thing, right, during the resampling process, bootstrapping, you can kind of correct for that error. All right. So that's all I had for you today. I've gone over time again, and I apologize. I'm going to blame magic and the fact that it's oh my god late. I hope that you managed to suffer through that with me, and if it's not clear, please come talk to us during discussions. Okay? Hasta la vista.